So welcome to Electronics for Amateur Radio Module 1, 2. This is a shorter module talking a little bit about mathematics, just what you need to know. So today we're going to talk about numbers, graphs, multiplying, dividing, variables, exponents, counting to base 10, counting to base 2, and we won't have a demo on numbers. We'll just have it here. So again, watch and ask questions, do it online, and we'll do some modeling shortly in another session. And do by building, and electronics is 50% lecture and 50% experimenting. So numbers are these are called real numbers, and they're basically zero, negative, positive. They can be expressed as fractions, like 1 3/8, or decimals 1.235. When we do the third module, which is geared more toward the advanced qualification, we'll talk a little bit about imaginary numbers and reactants and things like that. But for here, we're just talking about basic real numbers, which everyone uses every day. Nothing special about the numbers. And then we're going to talk about graphs. So to represent data, we're going to use a lot of graphs. Some of them are generated automatically, like on an oscilloscope or spectrum analyzer or even a radio. And we've got some pictures coming up. But then sometimes we may want to graph things. So down below is the x-axis on the horizontal, and on the vertical axis is usually called the y-axis. And we have numbers down here 1 to 6 and 1 to 5. So if I wanted to plot, let's say 3 2, that would take me right here to this point here, and then we would just plot things. And there's various different things we can plot. So when we start looking at some of the test instruments like an oscilloscope, it's basically amplitude versus time, and we get a sine wave, and here's a square wave and a sine wave and an oscilloscope. When we start looking at a spectrum, we get a spectrum analyzer here, for example. So here you got amplitude versus frequency. And even radios now display this. So here's the ICOM 705 radio, and it's got the frequency here, and then it's got a waterfall display and the spectrum scope here, so you can see where the signals are, and then this is just a representation of that signals over time, so you can see various patterns in the signal. Then other things we can do is, if we're looking at amplifiers, we won't actually be plotting this in this course, but in the advanced course, we'll be looking at it in more detail and actually maybe plotting some of this. But the important thing to know is that every amplifier has a curve, so you can express it in one of two ways. One is an output power versus efficiency, and as you go up, you'll notice that it'll drop off at some point, and this happens to be like around 60% for this amplifier. And what you want to do is operate in the linear portion of the amplifier, especially if you're doing single sideband. If you get up into this region here, you get distortion, and you can generate harmonics and cause some interference problems. Another way of looking at it is to look at input power into the amplifier and output power of the amplifier. And again, you get this curve that's linear part here, and this is where you want to operate. And then as you get up higher, you reach a saturation point and a compression region where your signal is not going to be look that good or sound that good, and you don't want to operate in this region up here. In a future session, we'll be talking about decibels and logs, but I've decided not to include it in today's session, not to get too confusing if this is your first introduction into into logs and exponents. So, what we're doing is basically multiplying and dividing numbers. And there's different ways of, you can write this down on a piece of paper. So 3 times 5 using an x equals 15. They tend not to use x because it gets into confusing with the mathematics. Or you can write it 3 bracket, 5 bracket equals 15. And then if you're dividing, they normally, instead of using the dividing sign, they normally have a slash. So this would be 15 divided by 3 equals 5. And then if we take it to the next step and introduce variables, basically you're using a number like x, y, or z, which is used in mathematics, or ABC. In this course, we'll be using things like volt, amps, and I for current, and E for volts, and R for resistance. But going back to the example here, 3 times 5 is 15. So I could take out the 5, for example, and say 3x equals 15, and ask, what is x? So, you would divide both sides by 3. So to leave you with x. So x is 15 divided by 3, which is 5. And then you could do the same thing for this equation over here. So 15 divided by y equals 5. So what you would have to do is solve for y. And in this case, y would be, well, you'd have to you divide both sides by 15, and then flip the thing around, and then y equals 3. So we'll be using this in Ohm's law, and this is all the algebra that we're going to be doing. It's just using variables and solving for one variable. The other thing that's important is exponents. And you may have heard of squaring or cubing, like 2 squared is 4, 2 cubed is 8, but we generally apply it to 10. So 10 squared is 10 to the second power, or 10 by 10, 10 times 10, which is 100. Or we can cube it. So 10 cubed is 10 to the third power, which is 10 by 10 by 10, which is 1,000. Or we could say, 10 to the seventh power. We would write it like this, 10 to the seventh. And that would basically be 10 times 10, 7 times. So if you count here, 1, 2, 3, 4, 5, 6, 7. And that would be 1 followed by 7 zeros. So 1, 2, 3, 4, 5, 6, 7. And normally we would call this 10 million. So that becomes important when we're dealing with capacitors and inductors, because they are measured in small values. And you can do the opposite. So if you write 10 to the minus 2, it's basically 1 divided by 10 times 10, which is 1 over 100, or 0.01. 10 to the third, 10 to the minus 3 is 1 over 10 by 10 by 10, which is 1 over 1,000, which is 0.001. And let's say 10 to the minus 7th power is 1 times 10 to the minus 7. So it's 1 divided by 10 times 10 times 10 times 10 times 10 times 10 times 10, which is 1 over 10 million, or 10 millionths. So this becomes important when we're dealing with small or large numbers. Instead of writing out all the zeros, we use exponents. And another thing that's interesting about exponents is that you can add exponents, and adding exponents is the same as multiplying. So if I have 100 times 1,000, and I don't want to use a calculator or keep track of all the zeros, I could just say, 10 to the second power plus 10 to the third power is 10. 2 plus 3 is 10 to the fifth. So it's 100,000. So that'll come in handy when we do some of the equations, especially with frequency. And then if you subtract the exponents, it's the same as dividing. So, if you wanted to take 100,000 divided by 100, you take 10 to the 10 to the fifth, 10 to the minus, divided by 10 to the 2. So it's 5 minus 2, which is 10 to the 3, which equals 1,000. So it just makes calculations a little bit easier. And if you have a scientific calculator, you have exponents on the calculator, and this is how you would use them. So now we're going to talk a little bit about numbers. And so we numbers are everyday numbers are in what's called base 10. So that basically means you count up to 9, and then after 9 it becomes 10. So when you look at this number here, let's say 182,736, if you were to write it out here, the first one would represent 10 to the 0, which is basically 1, 10, 10 to the 1, which is 10. 10 squared is 100. 10 cubed is here. 10 to the 4th is here. 10 to the 5th is here. So you can write the numbers down like this. So, you know, the 1 to the, so it's 1 times 10 to the 5th, 8 times 10 to the 4th, 2 times 10 to the 3rd, 7 times 10 squared, 3 times 10 to the 1st, and 6. And when you add all these things together, you end up with the same number, 182,736. So normally you wouldn't do this with base 10 numbers, which we use every day, but it becomes important when you start getting into digital stuff. And digital stuff is on base 2. And basically, there's only two states, 0, which is off, and 1, which is on. So if you look at base 2 now, this one represents either 1, 0 or 1. This one represents um, 2 to the first power. The third column here is 2 to the second power, which is 4, and then 2 to the third is 3, and 2 to the fourth power, which is 16. So if you had this number here, 11001 in binary, you would go through the same process. So it would be 1, this would become 0, this becomes 0, this would become 1 times 2 to the third, which is 1 times 8, which is 8, and then this is 1 times 2 to the fourth, which is 16. And then if you added all these things up, 1 plus 8 plus 16 is 25 in base 10. So that just shows you how some of the digital things work. So that's just basically for information about digital numbers. But you'll see sometimes digital numbers in articles and being expressed this way. So this is how to convert it back and forth. Of course, you can always Google, you know, base 2 to base 10 converter and Google and just convert it that way. So here, you know, when we get into counters, you know, we start counting, you know, if you want to have a 1 to 9 counter, and this is how, you know, you get your digital display. It starts counting, so it's 1, 10, 11, 100, 101, 110, 111, 1,000, and then it goes up to 1,001, and then 10 flips over to the second digit. So most systems are based on counting up to 10. Some systems are based only counting up to 8, and some are based counting up to 16. And this is if you're getting into computers and getting down into the machine language and the coding. I'm just giving you this information just to see what it's like. And then if you look at computers, and this is why you know, when you buy memory or speed or something, it always comes sort of in multiples of 2, and that's because it's based on the digital system base 2. So it's 2, 4, 8, 16, 32, 64, 128, 256, 512, you know, 1024 or 1K or 2048, commonly referred to as 2K, and then you also might get 4K and 8K. So that's how all those numbers come up. when you look at computers. And then a new term has come out. So 8 bytes. So each one of these is a byte. Is it becomes 1 bit. So sometimes they talk about bits, and sometimes they talk about bytes. And 8 bits equals 1 byte. So more to come. We'll talk about logs in base 10, which relates to decimals. So that'll be coming up in a few weeks. When we talk about power, we'll probably introduce decibels. And then if you will continue on to the advanced qualification, which will be module 3, we'll talk about imaginary numbers known as in electronics as J, or in mathematics as I. They're the same thing, but I stands for current. So that's why in electrical engineering they've gone to J. And then we'll get into a little bit about polar and rectangular coordinates and phase, what it actually means. Then if you take if you take that graph and put it in a circle, you get a Smith chart. And we'll talk a little bit about that and how to use it. And then we'll talk a little bit about base E logs when we look at the curves of capacitors and inductors charging. So that's coming up in advanced one in module 3, which will probably be like 6 or 8 months from now. And the thing is that you can express anything in mathematical terms. So depending on which textbook you look at, we're just interested in looking at the sine wave. What is the amplitude of the sine wave? What's the frequency of it, or what's the period? And then between two different signals, what's the phase between them? But if you're really interested, you can assign a mathematical equation to it. And this is, for example, a mathematical equation for a sine wave. And, amplitude is A. Then you take the sine of B, which is related to the frequency or the period. And this is where 2 pi comes into. Then you got X, which is basically just means the number here, plus C, where C is the phase, and then you take the sine of that, and then you can also have D if you want to vertically shift the graph up. So you can express everything in mathematical equations, and this is quite common when you're talking about AC power. But I mean, we're not going to get into this sort of thing, but it's out there if you're interested. And then for physics, they use they express it slightly differently, where this is velocity of x versus t, a function of x versus t, and then they use a similar equation, but instead of uh, B, they use wave number, and then they use W is angular frequency, which is related to 2 pi. And this is quite common in electrical engineering too. And then they have phase over here. So, again, everything can be related to mathematics. We won't get into mathematics unless it's required. So that's basically it for mathematics. Next week we'll talk about units, and then we'll get into doing some simulations, and then we'll talk Know Your Tinkercad simulations, and then we'll get into Know Your Multimeter, and then we'll actually get into circuits and build things and measure current and voltage and phase and things like that. So, any questions on mathematics? All right, let me stop the recording.